Thanks, Sylvain, and thanks to the organizers for the conference. It's been a great day so far. I haven't spoken at a conference in person for a very long time, like at least more than 6 years. So I thought talk about a lot of the bigger initiatives that have happened in that time. Have a bit of luck. This will forward. Yes. So I'm basically talking to you about some of the large-scale technical initiatives in this ecosystem, because it's an ecosystem with maybe 100 packages that almost everybody knows, and like many thousands beyond that. And to make these big ideas into a reality, it's an interplay between individuals, communities, and companies to actually make progress on some of the biggest problems, especially around performance and usability that we have. So the first one is maybe the smallest one, NumPy 2.0. Let's start there. So I started becoming a NumPy contributor in 2008 and became the release manager in 2010. And basically, the first thing that happened was this. So David was the release manager before me, and he figured out someone broke the ABI. So that resulted in a bit of a mess. As a result, the community started discussing how to fix this mess. Do we rip out all the things that caused the problem? But how do we then reintroduce them? And that resulted in, let's try NumPy 2.0. So the first time someone thought about that, I think, was in January 2011. And this was Charles Harris, better known as Chuck. He is still the NumPy release manager today. He is about 80 years old. It's absolutely amazing. But he said, let's do a 2.0 release in April or June. So, we'll get that done in a few months. Well, that ran into a few hiccups. So a year later, Travis had come back from, consulting to do more in NumPy again, and he had an intern who did a lot of interesting stuff and said, okay, we have new features, we need the stability, but we also need the new features. To introduce the new features, we really need a NumPy 2.0. Let's do that in January 2013. That didn't happen. So then there was a lot more discussion about it and said, okay, this Achilles heel of NumPy is really the C API. Because basically everything else depends on NumPy, and if you change NumPy in a certain way, everything just breaks, and that makes it really hard to experiment both in NumPy and also write an alternative to it. All right, so what happens if you make those changes that would cause it to be 2.0? We can see it because we now have a 2.0, so it's easy to try. So if you do UV pip install IPython and pandas, with the last version of pandas that didn't support 2.0, this is the error message that you get. And it's a bit obscure, but it basically says something about binary incompatibility. When you see that, okay, uninstall, try again, wipe your system, right? I think many of you may have seen this message at any point. So the less benign version of that is, things just crash. When you see something like Windows fatal exception on your screen, you know you're going to have a hard time. And this is what happens when you change the ABI. As a result, the NumPy 2.0 idea was basically shelved for almost a decade. No one even dared poke at it because of all the arguments and basically the impossibility of changing it and then taking this whole ecosystem of thousands of packages along with it. So to his credit, Sebastian Berg was the main person who started poking at it again, because he was doing a lot of maintenance and improvements in NumPy, and he couldn't do a bunch of them without changing the internals. And so I think the first time he brought it up was 2019. And he said, this will make our lives easier, let's just do it. And all the other maintainers said, no, that's really not a good enough argument. So he tried several more times, and then in 2023, he's like, hey, I brought this up many times, I really want to do it now. And he made a better argument, and he said, okay, maybe it's time. all the people who suffered from the old arguments are gone, and this could work. We have better packaging, so maybe we can make this work. So we had a meeting. We had a developer meeting. We prepared it well. We said, like, OK, if we have a do NumPy 2.0 to break this thing, what do we want it to look like? And we basically asked the whole community, everyone who wanted to join, open meeting, come here and tell us like what you think it should look like. Do you want to contribute anything? If so, what would you like to change? And do you then sign up to make that change? Well, so we basically asked, like, should it just be another release with a bunch of breakage? Or do we want to be really ambitious and like put in a lot of like shiny new stuff? It was a very like engaging meeting because this is a nice question to ask and like for people to provide their own answers to. So people stuck up their hands and said, OK, let's make it ambitious. So there were a lot of things that did end up, going into NumPy 2.0, which was great actually, because now the message to like everyone else who uses NumPy was not like, sorry, we had to break a bunch of stuff, please adapt to it. But it's like, no, here's like a great, a nice new thing with a lot of release. And oh, by the way, you do need to recompile everything. So please, add some pins in your ecosystem. So fast forward, like we basically had it done in January 2024, and then we had to basically wait. So we had other projects had to catch up to all the changes because we couldn't just release it without creating havoc. So we had to go out and go to all the other packages and basically help them adapt. So we did a lot of work, even to the extent that we had someone on my team go to Ralf and basically make an auto-formatter plugin for Ralf to automatically update to NumPy 2.0 syntax wherever possible, just to make it as easy as possible. So then we picked a release date, June 16, and that's kind of, we kept to it, so NumPy 2.0 was a thing. And then there was this really long tail. So we opened a tracking issue, like we tracked maybe 100 packages or so. At the time, we said, OK, now you can start to make a release that is NumPy 2.0 compatible. And I just closed the issue a year and a half later, like 4 days ago. And all but one package, I won't name and shame the one here, but there's the issue if you want to see. It took a year and a half for the ecosystem to catch up. But it went off smoother than anyone could have imagined in the 2010s. All right, so what did we get out of that? I think primarily like better usability. Like we really, from what did all the users get out of it, right? What did all the other libraries get out of it? Usability, like we cleaned up the Python APIs a lot. There's now a clear split between public and private. We also did the same on the C side, but that affects way fewer people. And then we added Array API standard support. So Lucas Colley gave a nice talk about it earlier today that a lot of you probably saw. So I won't explain here what it is. But I think when the library is that old, like you can add new features, but there aren't many like important gaps left. But what you can do is usability and performance. And that's true of all the like established packages, right? And for NumPy, I think it was usability that was the main one. And the other ones were like long-term maintainability, as well as like the motivation of some of the key contributors. Like some contributors who stopped came back, and some of the ones that really wanted to do it, like Sebastian, like eventually they got there, right? Because if you only ever say no to people, it's kind of discouraging. So I think we got a lot out of this release as a NumPy project and also as a community. There were also some new features, some performance improvements, but they would have materialized anyway. So I think they weren't the key point of this release. So in the end, this was a very, very large effort. And I think it couldn't have happened without individuals like Sebastian, like a few people on my team that worked on it for half time for a year. And then there was a very large group throughout the community that gave feedback, that reported bugs, rebuilt their own packages. And in the end, it was enough work that there were multiple funders of that work, because it couldn't have all been done in like Friday nights. So Quantside and NVIDIA, they employed most of the people working on NumPy. Then NASA did a lot of sponsoring, Chan Zuckerberg Initiative and Tidelift, and these are just the biggest ones. So I think, without any of these three groups, like this wouldn't have happened. All right, so that's NumPy 2.0, and that kind of set the stage for, the next thing I'll talk about, which is maybe an even more ambitious project, even though it only took 5 years so far and not 15, which is array type support. And that is basically performance. So we had usability, we had array API standard support in NumPy 2.0. We could now look at how do we get SciPy, scikit-learn, like all of these other libraries beyond that, running on GPUs in particular, because that's a question a lot of users have. So the idea is basically that rather than using NumPy specifically, you look at the array that comes into function, you see what kind of library it's from, you extract its namespace, so instead of NP for NumPy, you now can use XP, and then you can write generic code, as long as you're writing in Python. And that started in 2020, 2021, as an idea, like that would be great to do, and that would be basically the only way that you can ever have GPU support in something like SciPy or something like scikit-learn. So that message really resonated, I would say. And a lot of people helped design this standard and implemented it in their libraries. So after like a year and a half, we had full support in NumPy, support in QPy, PyTorch through a compatibility layer, and a lot of changes in PyTorch itself, as well as like 6 or 7 other libraries that were in progress or were co-designing that standard, so make sure that it worked for them. And some GPU libraries or libraries with JIT compilers inside had pretty interesting requirements that we would have missed if we would have just done it as the core team from like a NumPy and a scikit-learn and so on. All right, so there was a bit of a history there, but basically we did some early demos that, hey, it could work. This was some LIGO that just got the Nobel Prize, and they published Jupyter notebooks for completely reproducible data analysis, which was quite nice. And we had an intern at Quantside, Anirudh, who basically made some changes. He forked SciPy and some of the array library packages and showed that you could run it with PyTorch instead of NumPy, without almost any changes to the notebook itself, which really was the goal. No performance data yet, because it was really can this work at all? And then we started thinking about how do we actually roll this out? And then we figured the Python code problem was really not that hard, but it gets way harder when you hit some compiled code. All right, there's C, C++, Cython. There's a lot of Cython in a lot of packages, and Fortran, Rust, and so on. Right, that won't just magically go run on a GPU. So that was the almost more important problem to solve, at least for packages like SciPy. So we came up with an idea, and the CPU-specific code, if it's some C++ code, you can make it run on other libraries, Cython has memory view support, for example, right? So it doesn't have to be NumPy specific, but that's, so it might work with PyTorch, but it still won't work on GPU. So you need an implementation somewhere that you can call, and basically, how do you find and call that implementation without rewriting everything was the key issue. But after this 1.5 years or so, 2 years, we started to get to the point where we could look at the array consuming libraries, and through a grant, Thomas Fan did a lot of the initial work of getting it supported in scikit-learn. So here is a PR from early 2022, where he proposed it and then said, okay, here's an estimator to key things in scikit-learn, and showed how it can run with CuPy. And that was even before the first final release of the final stable release of the standard, which was end of 2022. Right, that happened, and Thomas then came back and said, okay, I can do this with PyTorch too. And so he added PyTorch support in scikit-learn under an experimental flag. And that showed that not only did that work, and the code looked maintainable enough, but it was way faster. It was about 2x faster on CPU, and it was almost 30x faster when you could run it on GPU. And you could run it on GPU without code changes or having like CUDA code inside scikit-learn or anything like that. Right? And that got like a lot of people in the scikit-learn community like enthusiastic. And long way to go, but it seemed like the right direction. A bit later, we started making the same proposal in SciPy, and we copied like a lot of the scikit-learn implementation and kind of the shared ideas. But the main point is like, if you give it a PyTorch array or PyTorch tensor, you get a PyTorch tensor back. If you give it a JAX array, you get a JAX array back, and so on. Right, so this would be a change in semantics. So this will, once it comes out of experimental stage, very likely require a SciPy 2.0 release. Hopefully next year. We're not there yet. There was also a paper, mid-2023, and you can see just from the names on this, these are lots and lots of people from different array libraries, some old-timers, some very new people. So it had a very wide buy-in in like how it was designed. All right, and once you put that all together, in the end, what you want is performance with few code changes. JAX came a little bit later because it has a very different design. Right? It has an internal JIT compiler and it's lazy, so it doesn't do in-place operations, for example. But we had a bit of a discussion like, is that worth it? But actually, it turned out it was, and the main reason is performance. You just look at this fairly simple SciPy function, and the NumPy version of it, with just some image processing, ran in 22 milliseconds. And then you could run it with JAX, it would go to 6 milliseconds. You could then JIT it, go to 3 milliseconds. And then you could do the same on GPU, and it would go down to 275 microseconds. That is 1,000 times faster, right? And that's code that was already using NumPy in a vectorized way. Right? So this is the kind of thing, why we want to go through all of this trouble. Okay, I'll skip over this quickly because I think Lucas showed this. But basically, this was a very nice benchmark where JAX, PyTorch, NumPy on CPU and GPU were all compared, and it shows similarly like it scales nicely when the array size goes up, and you can get to about like 1000x faster in some cases. Right, so it's under an experimental label today, but you can use it. Like it has CI, it's fairly stable. So if the hotspot in your own data analysis or whatever you're doing is in SciPy or in scikit-learn, it may be interesting to check this. You just have to set basically tick one experimental flag per library, and then it should work for you, assuming things are implemented. And if not, we'd like to know. Right, so I think NumPy 2.0 set the stage for this, and it gave us the usability. And now this is really giving us a lot of performance when things get supported, as well as composability. Right? Because in SciPy, in scikit-learn, and libraries like that, we still have to do a lot of work, primarily because we have a lot of compiled code. When you look at higher level code, like end-user code or pure Python libraries, it's much easier to switch over and support all of these, but usually you need all of your dependencies to also support all these array libraries. And I think similarly, this was an even larger effort. So you again had at the beginning, a few individuals that wanted to get this started, and then a very, very large group of people that wanted to help out and basically make this happen because the idea was compelling. But again, big enough that it couldn't have happened without funding. So I think it was very distributed. Like, these are like 8 different entities, some institutional funders and a lot of companies that all liked this idea and often came, to Quantside, where we do consulting, with a problem where the answer was like, well, you're actually trying to do something that is solved by this standard and this approach. And then they started up supporting it. So a little broader, I would say, than NumPy, where it was one team. This was really throughout, like, maybe, I wouldn't even say it was one community. Like, the NumPy, SciPy, like, scientific Python is a community. Like, PyData is kind of like very largely overlapping community. But if you look at PyTorch or you look at JAX, they're kind of their own whole ecosystems, right? Also a massive amount of developers and users. And they kind of all came together and, helped push towards this. All right, that brings me to the third, I think, big idea that's also about performance that's happening right now. Who's heard of free-threaded Python? About less than half, I would say. Okay, so this has been going on for a little while, and if you read Hacker News or that kind of thing, I think you've seen it. It now starts to get to the point where it's usable. And the basic idea is simple. You want to run your Python code in threads so that if you have a CPU with 20 cores, you want to be using all 20 and not just one. So we've always had threading in Python. There's been a threading module in the standard lib for essentially forever. And you can run multiple threads. But what happens is basically you can run one, and then it can switch to another, and it can run that, but it can't actually execute the code at the same time. So you really get mostly single-threaded performance. I'm hand-waving a little bit. Right? So, and the same is true if you write C code that uses the CPython API. So like NumPy and Cython like generate that kind of code. They can only, when they explicitly release the GIL, then you just have a pure C or C++ thread, and it can run like in parallel with other threads. So that happens sometimes with built-in functionality in NumPy, or when you do I/O, then you can really have things in parallel. But it's fairly limited, and often like you get these bottlenecks where exactly one thing is running on a single core of your CPU. Free-threaded Python, the idea is like, let's get rid of this global interpreter lock, this GIL, run everything in parallel. Right? So ideally, if you have 20 cores, we see a speed up of like almost 20x. That would be nice. Well, the idea is fairly simple to explain like this, right? So I'll jump straight to performance. Like, does it actually work? So these are all performance measurements over the last 6 months or so as things start working. So this is like a classic Mandelbrot set, which is a trivially parallel problem. So you could already do it in Python with multiprocessing, which isn't true for all problems, right? When they're no longer trivially parallelizable, or you have something, like an object that you can't pickle, then you can't really use multiprocessing effectively, but either way it's a bit clunky. So you see here that running this in threads rather than in processes, makes the performance scale almost perfectly until the number of worker threads that you use is the same as the number of physical CPU cores on your machine, which is exactly what you want. Right? What happens beyond that is kind of like not that interesting anymore because the curves are essentially flat. Doesn't want to show me the next slide. All right. This is an example with smallish NumPy arrays. That's made by Nathan, one of my colleagues, which was reported actually as a bug report from someone trying an earlier version of free-threaded Python, and say like, hey, this doesn't scale well. Like the yellow line, which was NumPy on threads, would like fall off as the number of workers increased. But here you can see that, again, like a factor of 1,000 better, and it scales nicely with the number of workers until it hits some constant rate. Right, something very different and a bit like less native to this community, I guess. Async I/O. So used a lot in web frameworks. It also had threading already, but as you can see with the GIL-enabled build, if you throw more workers at it, even though everything's supposed to be async, right? Remember that only one thread actually executes in parallel, so this doesn't scale all that well. With free threading, it scales almost perfectly until 6 physical cores, and then it keeps scaling when you start using the hyperthreads. So that's really impressive and like a 6x speed up or so. And for a web framework that just serves some request, I guess that's the metric, like be stable and serve as many requests per second as possible. So this was work by another of my colleagues, Kumar, who is also the maintainer of Async I/O. And this is really the type of result that we're doing it for. Similarly, he took that same setup and did a higher level benchmark where he did web scraping with beautiful soup of Hacker News stories and showed that Python 3.13, like the default build, single-threaded get 12 stories from Hacker News per second. You can do that multi-threaded in Async I/O, and you can get to 35, and then more than double the performance when using free threading with the same number of threads. That's not always true, right? Like, it's not that free threading is a magic bullet, but in many cases, like the basic intuition is like things run better in parallel, like translates really well to higher performance. Okay, so this is a result I borrowed from folks at NVIDIA, who did something very different. They did data loading with the PyTorch data loader on GPU. Right? They have an NVIMage codec, and you want to load data in parallel as well because you want to feed as much data as possible to your GPU. And what they found is that like the little bars there was that with multiprocessing, it almost did not scale. And the reason was something I didn't expect, and maybe they didn't expect it, is that you have a CUDA context, which is something you need to run CUDA on your GPU. And it can be large, it can be like a gigabyte or so. Right? And if you have multiprocessing, it's a completely isolated process, which means you need a copy of everything. So they need a copy of this CUDA context. So at some point, you have 8 gigabytes of copy of something really large that you need to run your CUDA kernels. And that's why the performance curve was essentially flat. It was spending all its time switching between these contexts. With threads, you can share memory. So then it did scale, and they found that where they were really not keeping up with Pillow, even though they had a GPU, they could now outperform Pillow, and it didn't scale perfectly, but it scaled pretty well. All right, last example. This is actually worth reading. This is an essay-length thing from Trent Nelson. Did a work when he worked on PyTorch, and is now at NVIDIA. But basically, he built everything on a free-threaded interpreter, kind of from scratch for PyTorch inference with GPT-2, running on a web server and doing inference. And the left plot, you probably can't read it, but it says parallel load test latency distribution. And the blue bars are no GIL, so the latency is about 200 milliseconds, and with the GIL, it's about 1400 milliseconds. So also almost an order of magnitude faster. And for similar reasons, right? You need only one copy of everything, and you can use Async I/O to really run multiple threads in parallel. Okay, so those are 5 different examples, and I think not everything works yet today. There are still libraries that aren't compatible. There are parts of the standard lib that are less used that are not even thread safe. So this is still very much in development, but you can see from these results it's very evident that things work and are significantly faster. And I think this is kind of what was expected when the free threading was called no-GIL when it was first announced and proposed. But I think that was the expectation. Like that's the point we'd like to get to. If we can do that and keep it stable, because that's the harder part. How do you make that all technically work? Right? When there are more opportunities, when you run everything in parallel, there's just more opportunities for things to go wrong. So this effort, like it's been going on since 2021 and has a very different development story. Like the previous two stories, I think, were maybe, initiated by one or two people, but it very quickly became like a crowd, and you can't say that one person was the, definitely driving this whole thing. Free threading was essentially for the first 2.5 years or so, like a one-man show from Sam Gross. He was also one of the original authors of PyTorch, and now he works on for Meta, basically trying to make this thing work. So he made a fork of Python 3.9 to start with, and then he forked like lots of other packages to work with that. And then later he rebased it to Python 3.12, right? So we get one Python release a year. So for about 3 years, like he pushed on this, tried to basically optimize the CPython internals design to figure out how you could make everything work. And then in 2023, he proposed a PEP, a Python enhancement proposal, saying like, hey, we can actually do this thing. And that removal of the GIL was tried multiple times before, and like basically never got to the point where it seemed feasible at all. So that this seemed feasible was a big deal. So it was accepted, like preliminary, and then more people joined in over time. Like more CPython devs started contributing. Meta, added more people to the team, so it wasn't just Sam. Meta also started working with us at Quantside to basically help not with the CPython part, but with, kind of what we did with NumPy 2.0 as well, kind of take this whole ecosystem along. Because there were like many, many packages that needed like, deep surgery to make it work with free threading. And that's not something like volunteers, maintainers would do on a Friday night. And then I think the Google Jacks team gets a little, honorary mention because they were not involved at first, but at some point they just decided to go, support this in Jacks and all its dependencies. So they fixed Bazel, they fixed MLIR, and that really accelerated it and also turned up like a bug report every day at some point. All right, so CPython is now in decent shape. A lot more to do, but like it's usable. And here's just to give you an impression, like some of the most important packages in our ecosystem when they first like did a release that had support for free threading. So CPython 3.13, right, was the first version that had free threading support. It was October 2024. So all of the packaging tools, as well as NumPy, Pandas, and I think that's it, were actually before the first Python release, they already had their compatible release out, which was like extremely early, and I think was because of Meta and Quantside working a lot on these projects. And then there was this long tail of other packages starting to get support. But you can see, for example, like this is still like, it looks like there was a lot around October 2024. And a lot of great work was done. But if you see Cython, for example, it's there like right towards the right end. And CFFI is like right on the edge. Cryptography is right on the edge. These are 3 of the most popular packages in the whole ecosystem. Right? So everyone else that needed Cython before was just using some nightly and kind of hacking around Cython, not really having support. So we're really still at the beginning of everyone else being unlocked. So now that all these packages are there, kind of most of your dependencies, if you maintain a package, like safe bet that one of these is in them, probably multiple, right? They now work. And there's a public tracker made by Hugo, one of the CPython core devs, that basically counts, automatically counts from PyPI, like, does it have wheels for free threading? So in May of this year, there were 59 out of the top 360 packages that had support. And September, what was that, 4 months later, it pretty much doubled. So it's going to go really fast now, and Python 3.14 is way more usable than 3.13. It's way more stable, it's faster, it uses less memory. So I think it comes out in exactly a week from now, right? So you can download it now. You can wait a week, but it is worth trying. Even if you don't use it in production yet, but if you want to have an interesting challenge, try it on your own project. Give that a try. So what are we getting out of all this, besides like a ton of work? Parallel performance for a range of use cases. So not everything's going to get faster, but if parallel computation can help you, this will help a lot. It will also make some applications way simpler to implement. GUI applications are an obvious one. I asked the Spider developers, for example. Spider is a scientific IDE written in Python, and they say like one of their top issues is working around the GIL, because they need a thread to kind of run the UI, and they need other threads to do something, right? But if they do anything heavy in another thread, the UI locks up, right? So you need a lot of work to work around that. With free threading, you no longer have to. So again, like I think these are the recipes for success, right? You need the individuals. In this case, I think there was just like one. Now there are more people who spend a ton of effort on it and did great technical work, and as well as community engagement. But basically, Sam was like persistent, for several years to actually get to the point of like, hey, this may work. Again, like large numbers of people throughout the community helped this. And then funding, like I think multiple companies starting, to give engineering time, significant engineering time to make this work. But I'd say here, like Meta, like is funded more than an order of magnitude more than everyone else combined at this point, probably. So I'd say, they really got it to this point, and I think, continuing to fund a lot of the work. So I think all of these are kind of ingredients that prerequisites for success. All right. Sylvain said I have 5 minutes, and that was 2 minutes ago. So I have a tiny, tiny demo. Really, this is all you need: a UV init for a test project, UV add the projects that you want. I did some image processing things, so I added NumPy, SciPy, JAX, Matplotlib, JobLib, Pooch. So with all the transitive dependencies, that is not a small list of projects. I tried it, it just worked first time, and I didn't handpick these libraries. So it worked on Python 3.14 free threaded. And then switch over to Jupyter Lab. Hope that's readable. So I wanted to just put these two together and see if we can do like the array type support with JAX inside a free threaded interpreter for SciPy. All right, so we are running a free threaded interpreter. And this is just an image detection, so edge detection. Plot it here to see what it does. All right, so there's an original image that's loaded, it's shipped with SciPy, and if you use some convolution, 2D convolution, you can detect the edges of the image. Right? And if you see here, it takes about 6 milliseconds to do that for one image of this size. Then, if we go back to the array type support, you have to generalize that a bit, so we import JAX. And then we rewrite this a little bit, so we add this retrieve a namespace here, and then we changed np.array to xp.array. And critically, we didn't change like the SciPy, right? So we now are able to call the SciPy function with a JAX array. Right? As you can see here, JAX array is coming out now. And how fast is that? Because it's only useful if it's faster, primarily. The same at this point. OK, sorry, that was the change function. So NumPy, and with JAX is actually faster. So it's like 3x faster at this point. Now, if you want to generalize that a bit, usually when you do data analysis, you don't have one image, you have a ton of images. So create a stack here of like 100 images. And then do the same, but batch it, right? So it's like the first axis of your 3D array now is 100, and you have to go through all 100 and do the convolution. Right? In NumPy, the idiomatic way to do this is create a result array, fill it with zeros, and loop over the images and fill the output. Right? And if you have 100 images, like intuitively should be about 100x slower. And it is. And now, if you want to use free threading for that, what you have to do is basically we have 100 images. I have 4 performance cores on this machine. So I split it in 4 threads that each do 25 images. Right? So you determine how many images go in one thread, and then you use a concurrent .futures thread pool executors that basically queue up this work so that it executes in parallel. And then this function takes the number of workers, so we can do this with 1 thread, 2, and then 4. I won't do more than 4 because it's not very useful in this laptop, because the efficiency cores don't really work all that well. Right, so you can see it goes not exactly, but almost 4x faster. This is the NumPy version with free threading, because we run it in parallel. Now with JAX, can do the same thing. So we modify this function some more. And I wanted to do this, and I didn't change the demo on purpose. Right? So I started writing the demo from the beginning, and I was like, OK, this isn't actually completely generic. So JAX has built-in support for batching. So the natural way to write this is use jax.vmap. Right? So I could have rewritten the function more extensively and do the same, but in this case, I'd say like the actual right thing to do would say like, OK, just use this one JAX primitive. So that the array standard, the API standard has like 160 functions or so at this point. Right? Batched operations isn't one of them. But if the library supports it, maybe I still want them. Right? So it's not like everything is magic with no work. All right. And it's doing some timings. Right? And this goes just as fast as the free-threaded NumPy version. And now we can use jax.jet on top as well. So it's like you jet the function that we used before. You have to then like use it once, so it can actually do the jet compilation the first time. It's really slow. Right? And now we can see how fast that is. And another 2.5 times faster. So with this relatively simple operation, we went 4 times faster, and then we were able to use jet with SciPy for another 2.5x more. All right, so I think that put it all together and gets us to the end of the talk. And I think, these big ideas, I think, are worth pursuing, right? Like, they're interesting, they're challenging, they take a lot of energy from a lot of people, they take a lot of money to fund them to do the work during work time. And they need community buy-in, and they will only get that when it's a really good idea that is not overly disruptive. Or if it's disruptive, it's really worth the cost. But when it is, I think it's extremely exciting to work on, and it's interesting for the whole community to get the benefits of this work. All right.
Wow, that's breaking my own rules. It's not just big ideas, it's moving mountains. It's really amazing. We really don't have much time, maybe for one question. So please raise your hand. OK, I'll have one. So multi-threading is really hard. And I can imagine so many cases where enabling free threading in a badly written code that was actually relying on the assumption that the GIL was there would break things. How can we live with it? Like, what's
yeah? So the in a way good thing is like that code was already broken, right? Because you already had threads, right? So they were just undiscovered bugs. But you're right, like it is much more likely to now hit these bugs. So you want the benefit, but now you're going to hit the bugs. And we've worked through like a lot of really bad code already. And there's a reason that free threading isn't the default yet, right? So it's now the first version that I would say is really stable and worth trying for a lot of people. 3.15 will be similar, just better, and I think 3.16 or 3.17 is most likely when it will become the default. So I think this whole like migration pattern will, there's thousands of packages to kind of better test. So better testing tools are the key, right? If you don't test in parallel, it's probably going to be broken. So we have to help the community with, writing CI jobs, writing the tools that it makes easy to have some PyTest plugin to automatically test a bunch of things. And even then, it's still going to be like hairy bugs, right? We had a lot of bug reports, and I think that's where that's the type of thing that's unglamorous. And when you get a bug in some, there's lots of packages that are 10 years old that have a maintainer that inherited this package that isn't truly familiar with all the internals, and may not have the time to wrap their head around this free threading thing. Right? So they need help, and that's part of, I think, where the funding and like a larger team of people that can help out with that is kind of necessary to get to the point where it's like you can confidently say like, okay, this is actually a win to switch to.
Thank you. Please, everyone, give Ralf another round of applause.